Lesson 8.3 is our hyperbolas. It's our final conic section we're going to be talking about. Officially by definition, like vocabulary definition, a hyperbola is the set of all points in a plane whose distances from two fixed points have a constant difference. If you go back and compare two ellipses, it was the distance from two fixed points have a constant sum. These have a constant difference. Now, it is still the two fixed points, which are called your foci. Okay, so you'll notice there we're still talking about foci, which is plural for focus. But here, what we've got is two fixed points. Okay, and it's constant difference. Okay, so constant difference between those pieces. Two fixed points are foci. Notice, so with hyperbola, it's two curves going outward. As you kind of glance here, my two curves going outward will either be what I call the horizontal ones, or they'll be the vertical ones. So we're not talking in a diagonal like quadrant 1 and 3 type thing. We're talking they're either going to be going out opposite of each other on the x-axis or on the y-axis type thing. We still, just like ellipses, have something called a focal axis. So the line going through the foci, from foci to foci, is called a focal axis. And you'll notice it right here that talks about a focal axis, so going from foci to foci there. The point halfway through the focal axis is called the center. So just like you had a center inside the ellipse, we have a center in between the two hyperbola. Okay, still going to be halfway in between the two foci. The points where the hyperbola intersects its focal axis are the vertices. So again, we have not one vertex, but two. And so these vertices are the points right here, kind of like a parabola. It's at that base of the curve, so to speak. So we have vertices. So I see a lot like parabolas in that you have the vertex at the bottom of the curve. The focus is inside the curve. The difference here is we have two of them, okay? If we compare it to an ellipse was kind of two curves going inward connecting. These are two curves going outwards. A little bit of new vocabulary. The chord line on the focal axis connecting the vertices is called the transverse axis. So when we talk about transverse axis, do I have a place I have it labeled? Not really, but the chord connecting the vertices is called the transverse axis. So transverse axis, think in terms of major axis for when we had major axis with the ellipse. Okay, a transverse axis and major axis are very similar in what they're doing. Okay, so like the major axis was the longer axis. It was the one that kind of determined which way our ellipse went. Here, I won't say the transverse axis is necessarily longer. That's a little bit different, but it is the one that determines which way our hyperbola goes. Okay, so we have our transverse axis. And then, instead of a minor axis, we have something called a conjugate axis. The perpendicular line through the transverse axis is called the conjugate axis. Kind of like the minor axis. It doesn't have a lot to really do with it, but it helps us to draw it. Okay, it helps us to find certain pieces. It's going to help us to find B, things like that. Okay, so that's a little bit of vocabulary. You've got some pictures up here to help you. Now, we have two charts, again, like we have in every other lesson, right? This one is hyperbola centered at 0, 0. Okay, so before we start throwing in the HK and moving things, we have a left column again. The left column is my horizontal axis. My hyperbolas go out from each other. So they open up left and right on that horizontal axis. Okay? The right column, we have a vertical axis. So my hyperbolas open up and down. Okay. Have you looked at the standard equations? What's different?
The Pythagorean relation.
Well, just start with, before we get to the Pythagorean relation, what about the standard equation? It went from what? What was in the middle? X squared over a squared, and it was plus y squared over b squared equals 1. That was the ellipse. For hyperbola, it is a minus. Okay? So that's going to be a one big thing. If they give you an equation, if you see that minus, you know it's going to be hyperbola. A plus is going to be an ellipse. Other than that, it looks very much the same. Okay? Over here on the left, y squared over a squared comes first. It's a little bit more specific because of the minus there. Focal axis, already kind of talked about that on the left column. It's x-axis, so they open up left and right. On the second column, it's y-axis, they open up and down. Foci and vertices, do those formulas look the same? Foci are still your C values, vertices are still your A values. Now, semi-transverse axis is A, semi-conjugate axis is B. If you remember last time, they said semi-major axis is A, semi-minor axis is B, yes? What I'm going to remind you is that when they talk about transverse axis, because they don't, in the problems, they don't tend to use the word semi, they just tend to say the transverse axis, and that transverse axis is going to equal 2A. Okay, just like the major axis equals 2A, the transverse axis equals 2A. And then the semi-conjugate axis is B. What's that mean about just the conjugate axis? It is 2B. Okay, so those are the pieces I'm going to throw on there again. Just that the transverse axis is 2A, the conjugate axis is 2B. What about this Pythagorean relation? Is it the same?
No.
Not exactly, is it? Last Pythagorean relation was a squared equals b squared plus c squared. This Pythagorean relation is c squared equals a squared plus b squared. This Pythagorean relation does happen to actually be the Pythagorean theorem. Okay, so just be aware. And then we have a new piece. We're going to talk about asymptotes. Okay, the asymptotes, the big time we worry about the asymptotes is when we're trying to draw the hyperbolas. They help us draw the correct shape of the hyperbola. So they have to do with the a and b values, so plus or minus b over ax, or y equals plus or minus a over bx, depending on which column you're in. Okay. Ready to look at example 1? See what we can do with it. Example 1. Ask us to find the vertices and the foci of the given hyperbola. 4x squared minus 9y squared equals 36. You had something like this similar with the ellipses. Should be a little bit easier this go around. I always feel like hyperbolas is a little bit easier just because we've been through the ellipses. What do we need to do to this equation first?
Divided by 36, get it equal to 1.
Okay. If you go back to the chart, standard form is equal to 1. So to make 36 become a 1, I'm going to divide by 36, which means I'm dividing each term by 36. Okay. 4x squared over 36 becomes x squared over 9, because 4 over 36 reduces to 1 over 9, minus 9/36 y squared. It's y squared over 4, because 9/36 reduces to 1/4. Now, if I want to go one step farther, I could write this as x squared over, what do you know about 9?
3 squared.
It's 3 squared, minus y squared over, what do we know about 4? 2 squared. Okay? I'm not saying you have to, but which column is this? Okay. Left column because what?
X squared over A.
Yeah, x comes first. Well, not because x is over a, but because x comes first. Okay, x squared comes first. And so with that in mind, because there's a minus sign, it's not about which denominator is bigger. It's about which variable comes first. Okay? So in this case, it is definitely an x squared over a squared minus y squared over b squared. And again, I'm not going to tell you that a is always bigger this time. Okay, that's a little trick that changes. A is not necessarily bigger. It's that minus sign is in the middle, so x definitely comes first here. Okay. We were asked to write vertices and foci, yes? Based on the fact I'm in the left column, what's my formula for vertices? Okay, vertices are going to be plus or minus a, comma 0. And that means foci. Just change out the a for the c, right? And foci are plus or minus c, comma 0. Okay. Well, that just means we need what? ABCs? What's A?
3.
Okay. A is always going to be your first denominator. Okay, it's under x in this time. We know A is 3. What's B?
2.
2, because it's always your second denominator. What about C? Do we know C?
Not yet.
Not yet. How do we find C?
Pythagorean.
Okay, it's that Pythagorean relation again. The only difference is that my Pythagorean relation changed this time, right? It's c squared equals a squared plus b squared. So c squared equals 3 squared plus 2 squared. 9 plus 4. If c squared is 13, then c is the square root of 13. Okay. Vertices are what?
3, 0, negative 3, 0.
Okay. 3, 0 and negative 3, 0. It is acceptable in that case to write as plus or minus 3, comma 0. Foci are?
Plus or minus square root of 13, 0.
Plus or minus square root of 13, comma 0. Okay, questions there? Okay, let's try example 2 then. Example 2 asks us to find an equation of the hyperbola. So we're going to be doing an equation with the given foci of 0, negative 3, and 0, 3, with a conjugate axis that has a length of 4. And they're going to ask us to sketch the hyperbola and its asymptotes. Okay? What kind of information are they giving us? What are some of the pieces that we can pull?
It's right column.
Why is it right column?
Because the foci is 0 plus or minus c.
Okay.
And the numbers it gives are on the right side.
Right here. Foci are 0, negative 3, and 0, 3. If you go up to that, the table, I don't know if I need to point this. I think you guys have figured this out. But right there, foci, there's that form, 0 plus or minus c. So that tells me that I'm in the right column. So 0 plus or minus c. It also tells me that c is what?
3.
C is 3, yes? Okay. I am going to go over here and write my equation. That my equation is, what do we say, right column, so y squared over a squared minus x squared over b squared equals 1. What else do you have pointed out?
Where B is.
Okay. B, conjugate axis has a length of 4, so what's that tell me?
2B is equal to 4.
Yeah. The entire conjugate axis has a length of 2b, so 2b equals 4, which means b is 2. We know b, and if we know c, what else can we figure out?
A.
We can figure out a. So back to that Pythagorean relation. Remember, it's different this time. C squared equals a squared plus b squared. Do your math. 3 squared equals a squared plus 2 squared. So what? I end up with a squared is 5. So that means a is the square root of 5. Do you guys know the decimal for square root of 5?
No. You don't need
We're going to need, because we have to graph, we're going to need to know it. Otherwise, I would say we don't need to know it. But because we're going to sketch the graph, it is going to be helpful to know the square root of 5. So square root of 5 is approximately 2 point something. 2.2. And again, the only reason I care about it is because I'm going to sketch the graph. That's the only reason I care about it. Otherwise, I'd say, whatever. Okay. Well, can we go ahead and write the equation? My equation, we already determined y came first, so y squared over a squared. What's a squared going to be?
5.
5 minus x squared over b squared. 4 equals 1. Okay. Okay, guys. Oh, yes?
So why do we not write it down like square root of 5?
Like square root of 5 squared?
Yeah.
You can as like kind of an intermediate step, but for final answer, we usually put it as what it is squared. Is that what you're asking?
Yeah.
Yeah, I just skipped that intermediate step this time. But yes, you could definitely start off by saying, okay, that's square root of 5 squared, and that's 2 squared.
All right.
But then when you square them, they're going to become 5 and 4. Okay? Anything else? Okay. Let's sketch a graph. Now, make sure you follow along here. Hyperbolas are a little bit different creatures. Definitely a little bit different than our ellipses. Okay. Now, with this in mind, let's see, what's our biggest value? I think about the only place, only place you really have to do is label out, I'm going to put tick marks about 3 out in each direction. I'm not going to use up my whole place, because I kind of need to be able to work outside of there. So I have tick marks going 3 in each direction. Now, we were given that the foci We're at 0, 3, and 0, negative 3, yes? So that means that my foci were where? On the y-axis, right? Right here. Those are foci. Or keep in mind that is also my C value. Okay. Now, those are foci. Vertices are on the same axis, yes? Vertices are on the same axis, but instead of being at C values, vertices are at A values. What was A? Square root of 5 or
2.2.
2.2. Okay, so I'm going to put a little point there at 0, positive 2.2 and 0, comma, negative 2.2. Those are my vertices. Okay, those are what my hyperbolas are going to go through. They are also, for the record, my A values. Okay. Now,
what's with the dotted lines?
we'll get there. We'll get there. Those are our asymptotes. I'm working my way there. The other thing we need are the B values. Okay. Similar to ellipses, those are the points on the other axis. What was my B value here? B is 2. So B is 2 is we're actually going to, on the other axis, put points at 2. Now, these aren't anything official. We're putting those points to help us draw our hyperbola appropriately. Okay? They're not a vertice, they're not an ellipse, or they're not a vertice, they're not a foci. They're there to help me draw the right shape. Now, okay. Before we can sketch the hyperbola, we need the asymptotes. And those dotted lines are the asymptotes. The dotted lines that form an X are my asymptotes. And with that in mind, we need those asymptotes to get the right shape of the hyperbola. Now, if you look at, if you look up in the chart, what's the formula for asymptotes? On the one we're looking at, it's plus or minus A over BX. Well, yeah, we can do that. But I really don't want to have to graph those lines. Okay? So, I mean, yes, that is, in our case, it'd be what? Plus or minus square root of 5 over 2x. Okay? But that's not an easy way to graph the line. Okay? But what we do have here essentially is kind of the slope of the line. Okay? Here's the shortcut I use over here. Go back to your graph. In order to draw my diagonal asymptotes, I start by drawing a box. My box goes through my A points and my B points. Okay, so right here, my box is going to go, it's just a dotted line box because it's just going to help me match up my asymptotes. So I have a dotted line through each A value and each B value. And it forms a box. Okay? That box really doesn't do anything other than it's going to set up my asymptotes. My asymptotes go diagonally through the corners, and it has to go through the center. Where's my center at? 0, 0. So I'm going to have an asymptote that goes through the center and through each diagonal corner of the box. I have an asymptote that goes there. I tend to start from the center and draw each direction. That's the whole point of the box, is just to get me to my appropriate asymptotes. Now that I have the appropriate asymptotes, I can draw my hyperbola. Now, this was a right column hyperbola, which way my hyperbola is going to open?
Up and down.
Up and down. And where's my hyperbola go through? It goes through the vertices. Remember your A values? That's going to be your vertex there. So the asymptotes help us determine how wide it is. So the idea is that my hyperbola runs out and alongside those asymptotes. Same on top as it does on bottom. Okay? Because sometimes our hyperbolas might be really skinny. Sometimes they might be wider. Okay. What do you think? Questions on that? Okay. Unfortunately, that's going to have to be our ending point. Because you guys know I can't get through another thing. You can start looking at the chart on the next page. But the chart on the next page, what? It looks a lot like the ellipse chart, doesn't it? Okay? It's the same variation. It's just now with our foci and vertices, we throw in HK. With our standard equation, we throw in HK. Okay? So we will pick up here tomorrow, go through those two examples at the bottom, and hopefully have time to get through an eccentricity problem. Okay? You could probably, if you're really motivated, you could look at the beginning of the homework that has to do with the, what do I want to say? The ones that are centered at 0, 0.